Hi and welcome back. So in the past video we were talking about all of these numbers for the atomic masses of given elements, and actually I'll undo that because I don't want to draw all over that name, but we were talking about the atomic masses for all these different elements, and we were talking about how these are weighted averages. They're weighted averages for the most common, based on the, or I shouldn't say the most common, based on the percent abundances of given of the different isotopes of these different atoms or of these different elements. The atomic masses that we have on the periodic table are weighted averages of the masses of these different isotopes that we can have. And in the past video, we had gone through, and I had done this example where we were looking at, scroll over to it, we were looking at hydrogen, and we found out that, what the mass that is on the periodic table for hydrogen, which is 1.0079, we figured out based on the percent abundance, and we didn't get exactly what the mass was on the periodic table, mainly because, and I explained this in the last video, but mainly because this number, the numbers that we see for atomic mass on the periodic table are in atomic mass units. They're in AMU, and as we talked about previously in the playlist, one atomic mass unit doesn't exactly equal the mass of one proton or one neutron. Even the masses of protons and neutrons, they're very similar, but again, they're not exact. And so sort of that error when we're dealing with a very light atom like hydrogen, a very light element, the atomic mass number that's reported on the periodic table has to be adjusted a little bit to compensate for that. So even though we figured out what the percent abundance was and what the weighted average of I guess the average atomic mass based on our two different most common isotopes of hydrogen, or our two different stable isotopes of hydrogen, it still didn't work out to be equal to what's on the periodic table. So what I want to do in this video is I want to take a look at another element, and it's not going to be totally equal, but it's at least going to be more equal. And we're going to look in this video at neon. Neon is over here. It's all the way over on the other side of the periodic table, and we'll talk more about this, but this family of elements is called the noble gases, and we'll talk much more about this in the future. It pretty much means, and this is a little bit of, I guess, the reason about why the periodic table is organized the way it is, but all of these elements in this column share very similar properties, and it kind of is a little bit of the reason why the periodic table is arranged the way it is. But anyway, sorry, I'm getting a little ahead of myself. So anyway, what we're going to do is we're going to figure out, we've got three different stable isotopes of neon, and we're going to figure out their percent abundances. So if we had, again, if we just had a big balloon, let me draw a better color balloon. Let's say I had a purple balloon. So if we had a big purple balloon filled with neon, we could say that the percent abundance in that balloon, and actually let me pull up Wikipedia so we've got the exact percent abundances. So this is just the Wikipedia page for neon. If you want to go there, I definitely recommend it. Wikipedia is incredibly helpful for lots of things with chemistry. But we're down here at the isotopes section. So it says neon has three stable isotopes. We have neon 20, which has a percent abundance of 90.48%. Neon 21, which has a percent abundance of 0.27%. And neon 22, which has a percent abundance of 9.25%. So let me actually just go ahead and copy those down. So this means that we've got neon, let me choose some good colors. So we've got neon 20, we've got neon, neon 21, and then what's a good one? Let's do blue. And then we've got neon 22. And all of these, we're going to have our atomic number is all going to be 10. Write that in. 10. And the last one, 10. So there we go. We've got 3 different stable isotopes of neon. And our percent abundances, which we just found from Wikipedia, this one is going to be, neon 20 is going to have a percent abundance of 90.48%. So we can see that this, that if we have a balloon full of neon, that this isotope of neon is going to make up the, and neon is a gas, part of the reason it's called the noble gases, or it's in the family of the noble gases. But we can imagine that 90.48% of the little gaseous neon atoms inside of our balloon are going to be this isotope. They're going to be neon 20. I'll just fill that up a little bit more. Then we had neon 21. We said that only 0.27% of the little gas molecules inside of our balloon are going to be this neon 21. I'll draw 3 of them. And then we've got this last stable isotope, which is neon 22. And we figured out that this percent abundance was going to be 9.25%. And so we can say maybe we'll have, I don't know, we'll have 4, 5, 6. That sounds about good. So you can see that the vast majority of the neon atoms that we've got inside of our balloon are going to be this isotope, neon 20. Then the next most plentiful, I guess, isotope inside our balloon is going to be this neon 22. And then finally, with a very small fraction of the abundance inside this balloon of our neon atoms is going to be this isotope of neon 21. So now, and pretty much what we're going to figure out is we're going to figure out what, and we've even got it right in front of us, what our weighted average is for the average atomic mass of our neon atoms, and pretty much what, the thing to, well, anyway, I'm getting ahead of myself. Let's just figure out this number first off. So we're going to say that we're going to take our atomic mass, so our weighted average is going to be, so we take the mass, we have a mass of 20, draw a better 20, we have 20 times the abundance, so 90.48 times out of 100. We are going to choose a neon 20 isotope out of our balloon. Then we're going to add that, so we add, and then, so our mass is going to be 21. And then 0.27 times out of 100, we are going to choose a neon 21 isotope out of our balloon. And then finally, let me give myself a little more space here. There we go. Then finally, we're going to add that. So our final mass of our last isotope is going to be 22. And 9.25 times out of every 100, we are going to choose one of these blue atoms, one of these neon 22 isotopes. So let's get out the calculator and figure out what the average, what the weighted average for our molar mass should be. So I'll clear that out. So we start off with 20 times 90.48 divide by 100. And then we're going to add to that 21 times 0.27 divide by 100. And then we're going to add to that 22 times 9.25 divide by 100. And we get, well, and it's a little bit off again. So again, there's a little bit of correction in this number because of the fact that one proton isn't exactly equal to one atomic mass unit, but at least we get a little bit closer number. So we figure out that the average atomic mass of the weighted average for the atomic mass of neon is going to be equal to 20.1877. I think that's what it was. Let me get the calculator. Yeah, 20.1877. So anyway, you can, and it's important to, I think, I guess, realize what this means, because you're not going to, probably in a general chemistry class, you're not going to be doing too many experiments with neon. But it's important to realize that if you were doing an experiment with neon, you wouldn't use an exact round number for your mass of neon, because you're not going to have a collection of neon that is 100% neon 20 atoms or 100% neon 22 atoms. You are going to get sort of, if you just go ahead and I shouldn't draw, I don't know, if you had a scoop, say you had some type of gas scoop, and that looks terrible, but if we just scooped out a whole bunch of atoms out of the center of this balloon, this is about the percentage of atoms that we would scoop out. This is the percent of the different isotopes of neon that we would scoop out. So therefore, the number that you would use if you were doing a lab and you were using neon, you would use this number. You would use 20.180. You would use 20.180 atomic mass units would be the weight, what you would consider for the weight of one atom, because that is the weighted average of what one atom would weigh inside of this collection. So anyway, hopefully you're finding this useful. And again, you're probably not going to be working too much with neon, but this goes for all of these different atoms in the periodic table. You'll probably be working a lot with, you'll definitely be producing carbon dioxide in a number of experiments you do. You'll definitely, I'd say, work with aluminum in some type of form. Let me do that better. So you'll definitely work with aluminum in some type of form. And so the number that you would use, and you might be using a different periodic table that might have rounded these numbers differently, but the number that you would use would be 26.982 for the mass of one atom, because, and we can see here that, the most common, what would you imagine to be the most common isotope of aluminum based on this atomic mass number? Well, it would be aluminum, and we know that the atomic number is 13. And this is a number that's really close to 27, right? So 27. That's probably our most common isotope of aluminum. And again, I'm not exactly too sure. Maybe I should actually, in a second I'll look it up on Wikipedia and just make sure that it actually is a fairly common isotope of aluminum. But the point is that even though this is the most common, or probably the most common isotope of aluminum, you wouldn't use just the straight 27 in a calculation if you were doing it for a lab. You would use this number, because this number, this 26.982, is the weighted average of what the average mass is of an atom inside a collection of aluminum. So anyway, hopefully that makes sense to you. I'm just going to look up aluminum real quick. So I'm going to say aluminum. Go to Wikipedia again, and I'll look up the different isotopes. There we go. 3 is isotopes. So yeah, aluminum 27 has got a natural abundance of 99.9%. So that's what we imagined it to be, right? And we said that based on this number of 26.982, that's really close to 27. So probably aluminum 27 had the greatest percent abundance. And we can see that we're pretty much right. Aluminum 27 has a natural abundance of above 99.9%. So anyway, hopefully you're enjoying these videos. I guess in the next videos, next bunch of videos, we'll actually start talking about. I've kind of over the past couple of videos been using the periodic table a little bit, and I haven't really given you an introduction to the periodic table. So in the next few videos, I'll hopefully give you a bit more of an introduction to the periodic table and all the different ways that you can use it. So anyway, thanks for watching, and I'll see you in a future video.